Woohoo! Welcome back. Thank you so much for coming back. I know some of this can be very intimidating. This is a bunch of new formulas plus physics plus word problems. So a lot of it's going on. But SpongeBob is here to cheer you on because you're awesome and you can do this. And I am trying not to make any corny force jokes. I allowed myself one in the last video, and that will be enough for me. If I start humming the Star Wars theme, I apologize. I was humming in between videos, and I tried to get it out of my system. But today, we're going to try the bane of my existence. I'm actually getting a little bit clammy and sweaty palms thinking about lifting cables up the side of a building. Honestly, I struggled with this in college. So here we go. You guys, you're here, I'm here. We're going to get each other through this. I've got a 200-pound cable, and it's 100 feet long and hangs vertically from the top of a tall building. The building is at least 100 feet tall, if not taller. So here's my building, and I've got my rope hanging. And what's really important is that it's actually hanging. So it's not sitting on the ground. And if you think about it too hard, you realize that the assumptions we're making are probably a little bit silly. But this is just the beginning of studying these topics. So this is much like in math when we say there is no air and there is no friction. So we're not worrying about the details of real life. We're just trying to get used to using these formulas, practice manipulating these formulas in very simple situations until you build up those skills. And then once you feel more comfortable with those, then your physics classes are going to throw a bunch of other details in at you. And it'll be super fun. It'll be super fun. I will be somewhere else when that happens, but feel free to let me know how fun it is. It's probably really fun. So we've got a 100-foot long cable, right? And it is hanging, and it is 200 pounds. Now, at this point, you realize that we're in foot-pound land rather than newtons and meters and joules. So we are in a different set of units. So make sure you reset that in your head. The other thing that we're going to assume is that this cable is completely the same all the way through. So it's not fatter some places and skinnier other places. We're going to assume that over the whole 100 feet, it is the same. And so that we can actually say at 200 pounds and 100 feet long, the cable weighs 2 pounds per foot. So it is the same top to bottom. That's going to be required to do this problem. Again, we're making assumptions to keep the problem simple because this is your first try at really getting into some of these formulas. Okay, so it can be very hard to work with it this way. You can work with it in Y, but what we're going to do, what the suggestion is that much like the way that they used to film the old-fashioned Batman from the 60s, we're going to put the wall this way. So here's the wall, which is kind of funny, but we're going to have the wall lying like this. Now, does this actually work when you start thinking about gravity? No, but we're going to do this so that we can use X and be able to visualize what's happening. So here's my Y-axis, here's my X-axis, and my cable is going to lie here. This is 100 feet right there. Okay, so that's sitting like that. Okay. So now, pardon me, SpongeBob, we're going to cut the rope into pieces. And each is going to have a length of delta x. Now, hopefully this is feeling very, very consistent and similar and familiar now. So we've got these little pieces that are delta x wide. And look at the ith piece. So this is x sub I. We'll call its distance to the top of the wall x sub I. So the distance here is going to be x sub I. Okay, that's how far away it is. The weight of the ith piece, which we'll use as the force needed to lift it up the wall. And again, gravity is pulling this way. So it's kind of weird. We've turned the whole thing that was up and down like this, where gravity is pulling down this way. Now we're changing the orientation just so that we can use x in a nice way. And that's the great thing about math, is we can move our axes to fit whatever situation we have. And a lot of times you are going to have to make choices about what you choose to make equal to x and what you choose to make equal to y, because that will either make your problem a lot easier or a lot harder. Now, why would hanging it down, right? We could just work in y, yes. But if we make this the origin, then all of these values are negative. Or if we make this down here the origin, we have to figure out how far above the x-axis this is. So it's just awkward. It's a lot easier to set it up like this. This is the way we do it. Okay, so this is the distance, each little piece. Now, I want to try to convince you, and SpongeBob is going to be here to convince me, to help me convince you, that this little piece of rope right here, or that little piece, sorry, I keep calling it a rope, it's a cable. In my math book, it was a rope. I'm having flashbacks, that's partly. So the cable, that little piece of cable, weighs 2 times delta x. So think about whether you think that is correct. So the cable weighs 2 pounds per foot. It's pretty heavy. And so if it's 1 foot, it weighs 2 pounds. If it's 2 feet long, it measures 4 pounds. So you can just multiply. What if it's 1/2 a foot? Then it's 1/2 times 2, it's 1 pound. So hopefully you agree that the weight of this guy, this little piece, is going to be 2 times delta x. The weight is just the force. Right? And so what we call the mass is not equal to the weight. That's just the amount of stuff. And then we bring in gravity. Weight is already the stuff with gravity included. So when we talk about the force, that is the weight. Because that's mass on Earth or mass on the moon or wherever we are. I don't know why you would dangle cables off of walls on Mars or the moon. If you're there, you should be doing other things. But there could be someone somewhere who wants to do physics when they're up, somewhere else on another planet. So that's the weight. So that's all we need to look at as the force. This took me forever to wrap my head around. So mass is not weight. Mass is just part of force, but weight, which is mass and gravity stuck together, is force. I know, it's a lot. Okay, shall we go to the next page? Okay, thank you for sticking with me. So the work is the force over a distance. So the force is just this little weight. And the distance, oh, I was too fast to throw that page away. How far are we moving it up? We're going to move it up x sub I. Because if this is the x-axis, wherever the piece is, right there, we need to move it however far it is. So this is the top of the wall. We need to move it however far out we are, whatever the x value is, that's how far we have to move it back to get it to the top. So we've got force times distance, which this is the force, here's the distance. So the work required to lift the entire, oh, and here I wrote rope. Oh my goodness. Oh no, this calls for, have I been writing rope? I've been writing rope. I wrote cable and then I wrote rope. Oh my goodness. Pterodactyl time, pterodactyl time. Oh my goodness. Oh, wow. Someone's getting fired today. All of my legions of assistants who helped me write these out, somebody's going to have to, I promise someone will answer for this. High crime. So the work required to lift the entire cable is just the sum of the work required to lift each piece, or from 0 to 100. Now, why is it from 0 to 100? Again, I keep putting this paper away and I should have it here. So this piece of the rope, how far does it have to go to get to the top? This part of the cable only goes 0. This piece of the cable right here, how far does it have to go? It has to go 100 feet. It has to go the whole 100 feet. A piece right here, that one's gonna, I don't know, I have to eyeball this. This will be like 35 feet maybe, right? So each little piece has to be lifted up a different amount. The way we did it, we set it this way, so we set it sideways. So each piece has to move however far away from the y-axis it is. So this piece moves 0, this piece moves 100, this piece, the way I wrote it, maybe like 60, 65 feet. This piece right here has to move up maybe like 20 feet. So each piece is moving a different distance, but the most they could have to move is 100 feet, and the least is 0. So we're going to move the little top piece of the rope here. Cable. Oh my goodness. And then this is the bottom of the cable, because it has to move the whole 100 feet. And then we put in, here's the work. Well, here's the force and here's the distance. So there's the work. You guys are amazing if you've gotten to this point. So let's see, I've got 0 to 100 of 2x dx. Now here's the thing, and this is frequently true. When the word problems are really difficult, frequently the math itself, like the calculus, this is not that challenging. This is very refreshing. Once you get to this point, how do you integrate 2x dx? It's just x squared. I mean, if you prefer, it's 2x squared over 2, but then that's just x squared, right? And we're going to take it between 0 and 100. And so that's going to be 100 squared minus 0 squared. So that's going to be, oh, pardon me, 10,000 minus 0, or 10,000. Now, what are the units? Do you guys remember? So the force, remember, was the weight. So that's in pounds. And the distance was measured in feet. So these are, and remember, it's backwards. So they're not pound feet, they're foot pounds. And that's the measurement of how much work you've done to lift the rope. I feel like a little bit lighter. I've shared my fear with you, and we've made it through together. I'm really Thank you so much. This is like therapy. Thank you so much, SpongeBob. We did this problem. Now, this was a nice short problem. The next problem. Okay, the next video. This is going to be a tank of water. This is a very classic physics problem. And it's basically going to be like the rope, but we're going to be moving a conical tank full of water. So rather than just a line of a cable / rope, it's going to be a little more complicated. So I definitely recommend you pause before starting the next video. Go give yourself a break. Go do something fun, whatever it is you enjoy. Get some exercise. Step out into the sun and blink a bit. Remember your sunscreen. And maybe remind the rest of your family that you still exist. They may have lost track of you at the beginning of this chapter. So go out, get some hugs, and if your family are furry, feed them and pet them and, all that stuff. And then have some fun, play some video games, do some art, dance around, sing, scream. And then come back and we're going to move some water. Woohoo. You guys are awesome. Math on.